Welcome to lecture 15. So in this lecture and the next we will discuss about modules and very basic properties of these things. Some of these, some other properties we will do in the exercises. Let R be a ring. So we have just come out of the computational part, the initial discussion of computational parts. So now from here onwards R is some arbitrary ring, commutative. By an R module, we mean an abelian group M with an action of R satisfying the following. So what exactly do we mean by an action of R? R cross M to M. Some map satisfying R cross M, some map from R cross M to M satisfying certain properties. 1. The element 1 of R should act on an element X of M as identity. Okay. So this is a notation. So R dot M is the notation for the element what we mean by R, this action. Okay. So what is R acting on? So this is just a notation. One can think of it as scalar multiplication. And second, okay, it should respect the addition in R Three, it should respect the multiplication in R okay. This is and 3 and 4 yeah oops, something similar to maybe I should call this 4, this is 3, just so that next time writing is similar to 2 and not 4, which is R times x1 plus x2 is Rx1 Rx2 plus Rx2, okay, and this is for all x, x1, x2 in M, and for all R1, R2, R in R. Okay. So if you think about it precisely, the definition, how we would formally, syntactically the same as the definition of a vector space or a field. Okay. So that's the most basic example. Okay. If K is a field, okay, then the word K module is synonymous with K vector space. I mean, a set is a K vector space precisely when it is a K module. 2. If for Z, what are modules over Z? The word Z module is synonymous with abelian group. Sorry, let me just go back to the definition. So M is an abelian group, and giving it an action of Z respecting these properties does not give it any extra structure. So Z module is precisely an abelian group. Okay, and one of the reasons, not one of the reasons, one of the advantages of study expressing various things in the language of modules as opposed to just studying ideals and quotient rings is that, first of all, there are things that we must address and not just ideals. I mean, there are objects that are genuinely modules and not ideals and quotient rings. Okay. But it also gives us, so this is a uniform language to prove, state and prove many theorems. So let me explain in a minute. R any ring, any commutative ring, okay, I an ideal, okay, then I is an R module, okay, and R mod I, the quotient ring, is an R module in the natural way, R times some R prime plus I. So this is an element of R. This is an element of R mod I. This we define to be, here's the definition, R prime plus I. Okay. So one advantage of discussing many things in modules is that, of course, one has to worry about them in general. Even otherwise, even if we just wanted to study, prove theorems about ideals and quotient rings, the language of modules gives us a uniform way of answering or stating or proving or going about proving them in a uniform way. Okay. 4. If phi from R to S is a ring map, in other words, that is S is an R algebra, okay, then S is an R module in the natural way, in the following natural way. So we will say through phi, the map, in the natural way. So we have to say what R times S is. So this R is inside R, this is inside S. We define this to be phi R. So now this is actually an element inside S times S. Okay. So here we are defining what this dot means, and here this is the product. So here we are defining this dot. Okay. Here this is the product inside. Yes, which is already given to us. Okay. So if you have a ring map, in other words, if you have an algebra, then that automatically gives a module structure. We can generalize that a little bit. Suppose N is an S module. Okay, so phi S as earlier. Okay. As above, then N is an R module. Okay. Through phi. Through phi. In other words, if you have R times some Y, this is inside R, this is inside S. Again, we want to define what this multiplication means. Define it to be phi of R, Y. Now, this is just the S module structure. This is an element of S and S module of Y. So, we can think of it this way. We have some ring R here and a ring S here and some module over that. We can look at this abelian group as an R module through this arrow. Okay, so this is another way, another observation about modules. Okay. Definition. So as soon as we introduce a new structure, new class of sets, we would like to understand the maps between, the functions between that set, those sets of that type which respect that, that structure. Okay? Let M and N be R modules. by an R module homomorphism or a homomorphism of R modules, or so one, okay, or just quite simple, or just plainly R linear map. Okay. From M to N, we mean a function f from M to N, such that, okay, but M and N are not just sets, they are such that they have an extra structure. So first of all, they have an underlying structure of abelian groups such that F is a group homomorphism. Okay. And f of R times x is R times f of x. So this times is in M, this times is in N, but it's all well defined for all R in R and for all x in M. Okay, so we can, if you had like R1 x1 plus R2 x2, then it's an abelian group homomorphism. So we can just take out the plus outside, and then we can apply this. Okay, so that which is okay, so this is really so just a remark here. Okay, for a field K, and K modules M and N, K module map F from M to N is exactly a K linear transformation. Okay. So really we are not doing anything, I mean, at least definition wise, we have not done anything new except just restating definitions in linear algebra. Okay, so that's the and the first, another observation that we would like to make is that the set of homomorphisms, let M and N be R modules. Okay. The set of homomorphisms, set of R linear homomorphisms, R module homomorphisms, form an R module. Okay, so we have to say what the map is. So it is multiplication that we have to define. Okay, and we have to check that it satisfies is a part of the definition. R times F. Okay, R times F itself is a homomorphism from M to N. So this is going to take some x, and you have to say what this x is. This is really F of R x. Okay, for all F from M to N, for all R in R, and for all x in M. Okay, so this is, so we'll write hom subscript R to denote that it's R linear M comma N. So this is like the statement that the set of linear transformations between two vector spaces from one vector space to another vector space is a linear vector space itself. Okay, so this is so one has to check that this satisfies the definitions, but please do that. Okay, now we want to look at special classes of modules. So the first thing is what is called a free module. Before that we go into a direct sum, since we talked about I forgot one more definition. R linear map f from M to N. So I am just continuing the notation. M and N are R modules. Is an R linear isomorphism if there exists an R linear map G from N to M such that Fg, so Fg is a map from N to itself, so this composite is identity, and Gf is a map from M to itself. This is the definition. And yeah, okay, so this is an isomorphism. Yeah. Definition. Let M lambda, lambda in lambda, be R modules. Okay. By the direct sum which is denoted as this, we mean, so this is what would sometimes we call the external direct sum. Okay. So we mean elements x lambda, the set of elements x lambda, lambda in lambda, okay, such that x lambda comes from, so this is at the lambda coordinate, we have, okay, we take an element from M lambda for all lambda, lambda in lambda, and for all but finitely many lambda, the entries are 0, and x lambda is 0 for all but finitely many lambda. Sorry, let me just okay. By the direct sum, we mean the set, which is all, which is really just take a long sequence, as many as there are elements in lambda, but don't take arbitrary elements everywhere. Take with this condition. Okay, so at the lambda coordinate, you take an element from M lambda subject to this condition. So, for example, if you take a polynomial ring in some finitely many variables, is a direct sum okay, where the indexing set lambda is Nn, okay, and M lambda is just R itself, okay, for all lambda. So this is one example. Okay, so you could have an infinitely many factors in the direct sum, but every polynomial will have only finitely many terms. So this is what. Okay, definition. An R module so this is an R module M is said to be free if it is isomorphic to to a direct sum m lambda lambda in lambda, okay, I mean for some lambda, where m lambda is isomorphic to R for all lambda in lambda. Okay. So it's just a direct sum of some number of copies, not necessarily finite, of the ring itself. So for example, K field, every vector space over K is free, is a free K module. Okay. So even this definition doesn't introduce us, it doesn't bring us anything new when we discuss vector spaces over phi. Okay. If R has a non-zero proper ideal I, for example, if R is not a field, it will have a maximal ideal different from 0. So the second statement applies to everything that's not a field. I mean, it has a meaningful content in everything other than a field. Okay, then R mod I is not a free module. Okay. So the reason is that if you look at the definition of a free module, because these are copies of R, there are elements in it. For example, you could take 1 in one factor and zeros everywhere that cannot be killed by, that cannot be multiplied to 0 by any element of the ring, any non-zero element of the ring. Okay. Well, that's not true here. So it's a statement about free modules. In free modules, there is always some element which cannot be multiplied to 0 by a non-zero element of the ring, by 0 by a non-zero element of the ring. Okay. However, if you look at R mod I, non-zero ideal I, any element of, from the definition, any element of I, any non-zero element of I will multiply every element here to 0. So this cannot be free. Say that M is finitely generated. In other words, again, we will abbreviate this as finitely generated. So this is the third context in which we are using the same abbreviation to mean the same. Okay. If there exists some finite subset of M such that for every Y in M, there exists R1 through Rn in R such that Y is summation Ri xi. Okay, so such a thing is called a generating set, and we are saying that there is a finite generating set. So then we say M is finitely generated. Okay. So for example, R Noetherian, I an R ideal, then I is a finitely generated R module. Okay. And just maybe 1, 2, K field, V a K vector space, V is finitely generated K module if and only if V has finite dimension. Okay. Another definition. Say that M is finitely presented before this definition, just a remark. So let G inside M be a generating set. Okay. Then there exists a surjective R linear map from the free, so I'll G to M, surjective R linear map, where by Rg we mean the free R module with basis G, So I didn't define basis now, it will be in the exercises. So immediately after this lecture, we should also work out that part about the basis. Okay, so G. So in other words, it's a direct sum of R with some basis element that is indexed by G, okay, to M. Sorry, I have not done the map. Surjective linear map phi from R to M such that with basis G such that phi of EG is G. Okay. Okay, so the map is EG here goes to G. G is an element inside M. Okay, EG is just a dummy element indexed by the generating set. Okay. So once you identify a generating set, then there is a map from a free module of that rank to of that many copies of R to M, and this is what. Okay. So this is. So therefore, M is finitely generated if and only if there exists a surjective map F to M with F, a free module of finite rank. That is a basis of finite size. Rank is the cardinality of the basis, and if you have a base of cardinality of if you have a basis of finite size, then it's called a free module of finite rank or a finitely generated free module, and M is finitely generated precisely when there is such a map. Okay. Definition: M is said to be finitely presented if M is finitely generated and for a surjective map F to M, where this is with F free of finite rank, okay, so such a thing exists because it's finitely generated. For a surjective map phi from F to M with phi of kernel of phi is finitely generated. Kernel of phi is also, I should clarify, this is kernel of a R linear map is an R module. I didn't explicitly state this. Sorry, didn't actually even define what kernel is, so let's actually do that now. Okay, so it's just with regard to the previous line. Okay. So kernel of, for an R-linear map, I didn't define it, but by now you may have guessed what it means by an R-linear map. For an R-linear map from M to N, kernel of F, which is the set of x inside M such that f of x is 0, is an R ideal, is an R module. Okay. So this is the okay. So the observation that we would like to make, and we'll quickly see an example of that, is the following. If R is finitely presented, if M is finitely presented, then it can be written as the co-kernel of a matrix. Okay. How? So recall that there is some, so let's assume M is finitely presented. So then there is some F1 free module surjecting onto M. Okay. F1 is free finite rank. Finite rank just means like vector spaces, finite dimension. Dimension is not a word used in this context, it means something else. Okay, so this is phi. Now, kernel of phi is again finitely generated. That's finitely presented, okay, finitely generated. Okay, therefore we can take some F2 which maps like this. Okay, now let's look at these maps. So this is a kernel sits inside here, so this is an inclusion. F2 is finite rank. Free. Both F1 and F2 are finite rank free. This kernel, okay, so this one surjects onto this kernel. Kernel sits inside F1 and the composite here. Okay, so we can take the composite. So let's call this map psi, and let's call this map I, and let's call this map phi1. Okay, so psi is surjective, I is injective, and we can take the composite. So we get a map like that. So we get a map psi1 from F2 to F1. This is R linear. So this you should check that this is R linear. Okay, and so these are free modules of finite rank. Okay, so F1 has basis, let's say E1 1 up to some E1 R1. This is the rank of F1. F2 has basis E2 1 up to E2 R2. Okay, R2 is the rank of F2. And now we can write this, express it the same way we do for vector spaces, express phi1 by the matrix Ri, let's call it Aij. Okay. So this will be R1 by R2 matrix, where what is the jth column? The jth column is where the jth, where we have so this is the definition of the Aij's. The jth, so jth column is phi of E2j. Okay, this is some Aij E1I. Okay, so this describes the jth column in. So this is so one of the reasons. So for most of the rings that we will work with, most of the modules will be finitely presented. One of the advantages is that it can be expressed in some finite data. So what is co-kernel? So we'll continue this discussion in the next lecture, but let me just finish this. What is co-kernel? Okay. Co-kernel means, so if f from m to n are linear, okay, then the co-kernel of f, this is called the co-kernel, is by definition n mod image of f. Okay. And the point here is that M is f1 modulo the isomorphic to f1 modulo the kernel. Because of this surjectivity and injectivity, image of phi 1 is exactly the image of I, okay, so which is the kernel. Okay, so here what we should observe is that image of phi 1 is image of I, which is equal to kernel of this phi. Okay, so therefore M is isomorphic to the co-kernel of this map. So this is what. Okay, so there is some advantage in working with these modules and these. Okay. So we will continue our discussion about modules in the next lecture.